Our first paper this afternoon is to be given by Donald Beck at General Motors, and he will talk with us about automotive exhaust catalysts, and we look forward to your presentation, Don.
Thank you. What I'll be talking about today will be a little bit of a modification from what appears in the abstract, but the subject matter is the same. Primarily what we're doing is continuing in our studies of the effects of SO2 on three-way catalysts to try to determine whether they're significant and under what conditions they occur, and if there's anything that can be done to abate the significance of the effect. And our more recent work has concentrated on looking at the effects of SO2 in automotive exhaust on palladium catalysts. Now, what I'll be talking about today will involve model palladium catalysts that were made in our laboratory. There will be some trends, though, that we've also seen with some commercial formulations. I'd like to acknowledge the assistance of a couple of co-workers, John Summers and Craig DiMaggio, for making the catalyst samples that we tested and for running some of the reactions. There's a number of reasons why palladium is of interest to study, especially recently, and that is its importance in reacting hydrocarbons at relatively low temperatures in comparison to platinum rhodium catalysts. And this is seen as one strategy that we can use to try to achieve the very strict hydrocarbon emission standards for California and eventually for elsewhere. It's also known that palladium is very robust to thermal deactivation relative to some more conventional platinum rhodium catalyst formulations. And finally, there has been a number of recent papers that have come out, and I'm sure there's a lot of work going on at the catalyst formulators and companies to try to enhance the NOx activity of palladium. In very early work, it was discovered that palladium is a very effective and active oxidation catalyst, but not terribly a very good NOx catalyst, not nearly as good as rhodium. But some of the base metal additives that have been added to newer formulations have enhanced that NOx activity. So there are a number of reasons why palladium is now being looked at as a viable alternative to platinum rhodium systems for three-way catalysts. What we would like to do is to try, though, to characterize the effect of SO2, which is naturally occurring in exhaust, and it comes from sulfur gasoline, on the activity of these palladium catalysts. We want to try to find out whether that impact is significant. We also want to find out if the effect is reversible, and if so, or if not, what conditions are necessary to try to get the activity recovered. This second point is important because in some prior work that was done in our laboratory, we compared the effects of sulfur on three-way catalysts that contain platinum rhodium and three-way catalysts that contain platinum palladium and rhodium. And it was discovered that for platinum rhodium systems, the effects of SO2 were almost completely reversible. But for the palladium catalyst, the effects were found not to be completely reversible. So this is an effect that we'd like to focus on in a little more detail. So just to outline what I'll be speaking about, I'll give you a brief description of the experimental setup that we use. Then I'll talk about the effects of SO2 on the activity of several palladium catalysts as a function of temperature to try to get an idea of the light-off. Light-off is sometimes used as a term to describe the 50% conversion temperature of a catalyst. And it's important as the car warms up and the gases heat up, the time to reach light-off is an important region of time in which you'd like to minimize to try to get the emissions down. That's where we can make the most, probably the most significant impact on lowering emissions is during the cold start cycle of the car. We also want to look at the effects under on the activity under warmed up conditions, and for our case we'll use 500 degrees C. And then I probably won't have time to show much of the results, but I'll just touch on the conclusions that we've been able to make, where we've looked at the effects of SO2 on the activity under net reducing or rich conditions versus net stoichiometric or net lean conditions. And finally, I'll probably just summarize what we've been able to find out about how to recover the activity. We studied 3 catalysts. These were made up for a previous study in which we looked at the lean activity of several palladium and platinum catalyst systems. But there are 3 of interest that we want to focus on. One is the palladium-only catalyst. One contains 5% weight cerium, and one contains 8.6% weight lanthanum. This latter catalyst is of interest to study because it's been reported in the literature for a number of years now, primarily from the work done at Toyota and more recently at Ford and other locations, that lanthanum can significantly enhance the activity for palladium under rich conditions, and particularly for NOx activity. And there have been a number of mechanisms proposed for why that is. There is certainly an important strong metal support interaction going on there, and we'll provide some additional evidence for that later in the talk. We are evaluating the activity of these catalysts using a laboratory reactor. But the reactor is set up to try to mimic as close as possible real exhaust conditions that we would see out of a typical V6 engine. So we have a gas flow bench where a number of gases are introduced and finally directed into a heat exchanger area and then into a catalyst bed. So we're heating up the gases, not necessarily the catalyst. This gives us a better control of catalyst temperature, particularly in experiments where we ramp the temperature up to look at light-off. When you reach light-off, there's an exotherm that occurs, and if the catalyst is placed inside the furnace, we tend to get a rapid jump in temperature, whereas just at the exit of the furnace, it's a fairly smooth function. We can also switch some of these gas feeds between a bank where we set up a net oxidizing or lean environment and a net rich or net reducing environment. And this switching valve switches between these 2 gas feeds on the order of 1 to 2 seconds to try to mimic the closed loop operation of the engine. So we're always cycling about the stoichiometric point for many of the experiments that we conducted. Finally, we can characterize the reactant concentrations or the product concentrations by directing a tapped flow into a string of analyzers. These are gas analyzers that are typically used for exhaust emissions benches. The conditions that we use in the gas flow for light-off and for the warmed-up converter activity test are shown here. These again are typical of what we would expect to see from one of our V6 engines. And the oxygen I show here is a 0.6% net. It's actually switching back and forth between 0.2 and 1%, again to mimic the closed loop operation of the engine. And there are a number of concentrations of sulfur that we've chosen to use, all of which are typical of what you would find if you were to use commercial grades of gasoline that you can find out in the markets. You can multiply these numbers by roughly a factor of 15 to determine what, or to arrive at the sulfur concentration in the fuel itself. So 30 parts per million roughly corresponds to about 450 parts per million of sulfur in the fuel. 20 corresponds to approximately 3 million. And 5 corresponds to approximately 45, which is near the standard specification that the California reformulated fuel will contain. If we look now to the effects of sulfur on the light-off activity for palladium only, and again, I'm just going to focus on the thermally aged catalysts. To digress, these catalysts have been aged by subjecting them to a cycle flow that's cycling between net oxidizing and reducing conditions at 1,000 degrees for a period of 4 hours, and that's a fairly severe aging schedule for our laboratory. But what we've been able to find, and again, I also showed the light-off activity of the fresh catalyst for comparison purposes. If you were to compare the fresh light-off to that of the aged catalyst, but with both being tested with no sulfur in the feed, you find that aging causes an increase in the light-off temperature for hydrocarbon CO, and it really degrades the NOx activity. This increase is on the order of about 30 to 40 degrees. Now, if you were to take the aged catalyst and then add 30 parts per million of SO2 to the feed, you further increase the light-off temperature by about another 30 to 40 degrees. And what I want to stress here is that the effect of adding sulfur to the feed is comparable to the effect of severe thermal aging of the catalyst. So it is indeed a very significant effect. The other thing I'd like to point out is that if we run the test with 30 parts per million sulfur in the feed and then take the sulfur out of the feed and repeat the test, we find that, and this is very difficult to see because it's a thin dashed line here, we find that we get some recovery of activity, but not complete recovery. In fact, we get about half the recovery back to the original light-off temperature of the catalyst. So there is a reversible effect of sulfur on these catalysts, and there is an irreversible part of the effect. And this is very unlike what we've been able to see on platinum rhodium systems, where the effect of sulfur is near completely reversible. Okay, if we turn to the catalyst which contains cerium now, and again, we ran the same experiments, each one with a slightly different amount of sulfur in the feed stream. We find again that on going from 0 to 30 parts per million of SO2, we get an increase in the light-off temperature. And again, it's on the order of 30 to 40 degrees centigrade. So with cerium in the catalyst, we're still seeing a significant degradation in the light-off activity. Another interesting kind of sidelight to this is that we have seen in the sample, aged sample, with no sulfur in the feed, a slight increase in the light-off temperature compared to the palladium-only catalyst. So there is a little bit of an evidence for hydrocarbon and CO inhibition effects by having a cerium present. This has been observed by a number of other researchers. The cerium, though, in the aged catalyst seems to enhance the NOx activity, particularly if there's no sulfur in the feed stream. When you add sulfur in the feed stream, it really makes no difference whether you have the cerium present or not. If we then turn to the catalyst which contains lanthanum, we find, first of all, if we look at the light-off behavior with no sulfur in the feed, we've got much lower light-off temperatures, particularly for hydrocarbon and CO, and we've got enhanced NOx activity, particularly in the low-temperature region, with lanthanum present in this catalyst. If we add sulfur to the feed stream, we do get an increase in the light-off temperature. So again, there's a degradation in the light-off conversion for hydrocarbon and CO, and there is a significant loss of NOx activity just by adding sulfur in the feed stream. So again, the beneficial effects of lanthanum can be partially offset by adding sulfur in the feed. However, if we do this experiment where we add 30 parts per million sulfur and then take it out and then repeat the experiment, we get more recovery of activity than we saw in the palladium and the palladium-ceria catalysts. So the irreversible poisoning effect seems to be less important with lanthanum present in the catalyst. Now, these phenomena that we've observed are fairly consistent with some of the published literature, which suggests there's a strong metal support interaction that can occur, particularly if you're able to form the spinel, the lanthanum aluminate. It's been suggested further that the lanthanum preserves the activity of the palladium by preventing the formation of hydrocarbon coating on the surface, and that allows the palladium to maintain better NOx activity. And there may be other promotional effects as well. As we'll see with the warmed up hot activity, that seems to need to be the case. But the presence of lanthanum does tend to give us an improvement in the general activity. Okay, now turning to the steady state performance, we do an experiment in this way. We have the catalyst heated up to 500 degrees C, and we have a cycling stoichiometric gas mixture running through. And at some point in the experiment, we add sulfur to the feed. We're starting with 0 sulfur. We'll add sulfur to the feed stream, and that continues for some period of time. Then we take the sulfur out. So this allows us to determine the steady state impact of SO2 on the activity. And it also allows us to determine approximately what recovery we can obtain by taking sulfur out of the feed. And that gives us an idea of the warmed up reversible versus irreversible poisoning effect. And what we see is a very dramatic impact on the NOx activity, especially if you look at these scales. But it's important also to note that even though the hydrocarbon conversion efficiency is only decreased from 98 to a little above 95%, this translates into an increase in the tailpipe emissions of about 150%. So even though this may on the surface appear to be a very minor effect, it turns out to be a very major one in terms of the impact on actual hydrocarbon emissions. And this is very important to us because it is the very low hydrocarbon emission standards that we're trying to obtain by using these palladium-based formulations. If we then turn to the catalyst which contains some cerium present, we find that upon adding sulfur dioxide to the feed stream, that there appears to be a much greater impact, especially on the hydrocarbon and CO emissions. It's much more deteriorated. The impact on the NOx emissions is approximately the same as for the palladium-only case. There's something else that's interesting to notice, and that is, if you remember from the palladium-only case, when we add sulfur to the feed, the impact on the conversion efficiency was fairly instantaneous. Whereas in this case, we have a fairly gradual or much slower impact increase in the impact on the emissions. We think this is related to the interaction between SO2 and the ceria contained in the catalyst, that there's either a much slower kinetic reaction or taking place, or there might be something going on with the transport phenomenon. But we think it's more of a kinetic effect. Whereas in the palladium case, we have more of a direct interaction only with the palladium. In fact, we think the reason why these decreases are much larger in this case is that it's an additive effect. Not only is sulfur dioxide interacting with the palladium to poison it, but it's also interacting with the ceria, and it may be influencing any interaction between the cerium and palladium. We really don't understand the nature of that interaction very well at all. In fact, we want to try to attack and address these kinds of issues with the characterization study, which we're carrying on now in our laboratory. The other thing that's interesting to note is that we don't get very much recovery, especially at the higher sulfur levels, and particularly with CO. even though it's harder to tell on the hydrocarbons, there is also not a complete recovery of activity when we take the sulfur out of the feed. Finally, if we look at the steady state effects on of sulfur on the lanthanum containing catalyst, we see the same kinds of trends. We see when sulfur is added to the feed stream, there's a decrease in the hydrocarbon conversion efficiency as well as CO NOx. But the overall magnitude of the impact is much lower than what we observe on palladium alone or palladium with the cerium-containing catalyst. This suggests to us, and also notice that the impact of the sulfur on the activity is again a very gradual decrease. This is similar to the effects that we saw with the cerium-containing catalyst, and it suggests again that in this case the SO2 is interacting more with the lanthanum, but not really much directly with the palladium. Now it's been suggested from previous work that the lanthanum is somehow protecting the palladium, and it's been demonstrated it protects it from hydrocarbon coking. Perhaps in this case it's also protecting it from a direct interaction between SO2 and the palladium surface. Maybe it prevents the SO2 from adsorbing and dissociating on the surface to poison it. We still have yet to really characterize that, but we're planning to do that with some surface science studies using XPS, X-ray diffraction and temperature program desorption. Well, just to touch on the effects under different conditions, we have run some experiments. Let's see if I can find this. Okay. We have run some experiments where we have varied the stoichiometry of the gas mixture in a stepwise fashion, and what we do is measure the conversion efficiency. This is like a sweep type test that many people use. What we discover, and there's some general truths about this that are true for palladium only and for palladium with cerium present, is that the impact of SO2 seems to be greater under rich conditions than under lean conditions. And in fact, we see that seems to be borne out here, particularly for hydrocarbon conversion, and even more so for the NOx conversion. In fact, what we have found for palladium with cerium present as well is that any beneficial effects that we see in the promotion of palladium for activity, and we see those effects with no sulfur in the feed, by seeing a very high conversion efficiency that comes way out to fairly rich or reducing mixtures. Any beneficial effects of the lanthanum and the ceria are essentially negated by adding sulfur to the feed stream. So we note that we're not exactly sure how that interaction works, but it's possible that the sulfur is totally reacting with the lanthanum or the ceria to prevent it from promoting or interacting, or even allowing the oxygen storage and release capability to take place. So that reduces a lot of the activity in rich conditions. In fact, another researcher in our laboratory has recently found that it takes very small amounts of sulfur in the feed to completely wipe out the oxygen storage and release capabilities of ceria in a typical three-way catalyst. Finally, I'll just touch on this. We talked about an irreversible effect of sulfur on activity and a reversible effect. The irreversible effect seems to deal with the interaction between SO2 and the palladium directly. And it may be a more vigorous reaction than simply dissociation of SO2 on the surface and formation of adsorbed, chemisorbed sulfur atoms, that it may actually involve some kind of reaction. We've done a number of studies where we've looked at X-ray diffraction of these catalysts, and in some cases we've been able to detect a palladium sulfide phase. It's not a very crystalline phase. The domain size are very small, but it seems to suggest there's a much stronger interaction than what we find occurs with the interaction between SO2 and platinum and SO2 and rhodium. To try to recover the activity from this irreversible poisoning effect, we've done a number of other treatments. In this case, what I'm showing is the conversion efficiency for hydrocarbon CO and NOx, and how it decreases when treated with 30 parts per million of sulfur in the feed stream at stoichiometric conditions. If we then afterwards treat in a feed stream that contains no sulfur in the feed, and we increase the temperature of these treatments, these are 10-minute treatments, up to 700 degrees, that you really have to go up to about 650 to 700 degrees to get full recovery of activity. So this means you have to go to very high temperatures to completely reverse the effects of SO2 in influencing the activity here. If we do these treatments in rich conditions, however, we find that we can recover the lost activity at a somewhat lower temperature. So it takes rich conditions to do this. We've also done this with lean conditions and found that it's very difficult to recover this activity under lean conditions. So there's a preferential need to run the catalyst in rich or reducing conditions in order to reverse this so-called irreversible poisoning effect. This interaction we have to look at again in our characterization studies a lot more closely, but we hope to try to do that in the near future and hopefully report on that. So I'll just finish by showing some conclusions. We've been able to find very significant effects of SO2 on the activity of these palladium model catalysts. We've done similar studies with commercial palladium catalysts which show similar trends, but perhaps not to the same impact. We've also been able to show that the nature of this impact is significant enough to be comparable to severe effects of severe thermal aging. It seems that the NOx activity is affected the most by the presence of SO2. Although we have shown that the hydrocarbon emissions in terms of breakthrough catalyst can be increased by very large percentages, and you have to essentially blow up the conversion efficiencies to really see that. So this is a very significant effect that we need to overcome. And finally, we've determined that using lanthanum catalyst seems to inhibit the effects of SO2 the most of all the three catalysts that we studied. This seems to be fairly consistent with what's been reported in the literature, with a strong metal support interaction between the lanthanum, or what may be lanthanum aluminate, and the palladium in terms of preserving the palladium's activity, keeping it from hydrocarbon coking, and inhibiting the direct interaction of SO2 with the palladium. So with that, I think I'll quit and try to answer any questions.
Thank you, Don. Yes, we have time for questions. If you step to the mic.
Sure.
Hi, Jordan Langford with Neighborhood. I just have a question about your aging cycle. That was with SO2 or without SO2?
The actual thermal aging was done without SO2.
Can you please speculate as to what you would see if you did the aging cycle with SO2?
Well, that's a very interesting question, and in fact, I wish that we had done so. However, I think what might have